I work at SRK Exploration. I expect a lot of you already know SRK. For those who don't, I believe we're one of the largest mining consultancies in the world, over 1,700 technical personnel worldwide. SRK Exploration is the only discipline-specific group in the SRK group. Obviously, we're exploration. All the others are regional designation. There's about 30 of us. We're all geologists based in Cardiff in the UK. We have a branch office in Johannesburg also. And Mark alludes to the fact that there's perhaps not too many pictures of rocks in this presentation. In fact, I'm not sure if there's any. It's a good reason for that, because I'm going to talk about prospectivity, which is generally this is something we're doing before we even hit the ground. This is, trying to answer that question of where should we explore, really. This presentation uses examples from West Australia throughout this picture. We're going to go through a few different models, and they all basically using the same West Australian data set, which is basically all the free data you can get for Western Australia. There is one data set in there which is private. But if you did wish to recreate this, you could probably do this at home with the free data, given enough time. Okay. Let me get my points up. Okay. So, a bit of scene setting. Now, when I was trying to work out how to make an engaging presentation, I was told you should start with a shocking statistic. So this is my shocking statistic. Exploration has a bit of an efficiency problem. So on this graph here, this is global gold exploration. Each year we spend in and around $3-4 billion globally on gold exploration. This bottom line is actually just segmented just the grassroots part of that, which is about half of it. But if we look at the value we get out of exploration, that's this blue line. It's consistent. Well, I was going to say consistent below. There was a blip where it was about $3-4 billion in gold exploration, and each year we're getting about $1 billion out. That's calculated as the ounces we could discover each year, multiplied by the average transaction price for M&As during that period. This is all data from S&P. So really, this should be a big problem for us, and should keep explorationists up at night. And so that's where basically. So if we're thinking about why we're inefficient, the main reason is because we spend a lot on unproductive exploration. That is exploration which doesn't result in an economic discovery. So hopefully prospectivity can help us direct just to areas where the exploration is worthwhile and increase efficiency in this regard. So one of the things I think about exploration is we have this ratio. We have this discoveries to targets ratio. Lots of figures get bandied about this. 1 in 1,000 seems to be the one that most people sort of talk about. Really, to improve exploration, we need to improve this ratio. We need to have get this into 1 to a few hundred. I don't think you can get down less than that. But and so conventional prospectivity up to now, we've been sort of concentrating on the 1, which has probably been a bit of a mistake. Really, I think to get some really good improvements in exploration, we need to reduce the 999, or failing that, spend less money on the 999. So I'd like to try and keep that in mind as we go through the presentation, because that's sort of my philosophy. The sort of current play of prospectivity is that I think we're in a sort of developing phase for it. There's been a bit of confusion between prediction and detection. Really, predicting deposits involves understanding the complex relationships between different geological layers. Deposit detection is not so much that, and really things like machine learning, prospectivity models, etc. They can really be effective at the predicting. I don't believe they're fantastic with the detection. I mean, they can add a little, but that's not really their forte. There's also been a bit of a focus, I think, in recent years on treating prospectivity as a sensitivity problem. This may come because we have this comparisons often with things like medical imaging. People trying to scan for cancer, let's say, predict cancer. That's a sensitivity problem. You're trying to get as sensitive as possible. We're not trying to do an exploration. Exploration is a false positive problem. We have too many false positives. We actually probably capture quite a lot of the actual deposits. We're just capturing a lot of noise along with it, and it's trying to reduce that. Prospectivity also has a very strong scale dimension, as does all exploration actually. When we're in that larger regional scale, we're in prediction mode. That's when prospectivity can be most useful. When we're at the deposit scale, the target scale, we're in detection mode. Take it right down to extreme and a drill hole, you're actually trying to actually intersect in mineralization. It's not to say that prospectivity doesn't have some role at the deposit layer, the deposit scale, but I think it's much less than it is at the regional scale. So what I want to show is how we can integrate prospectivity to sort of get away from what we've been doing in previous exploration and use it to try and answer some of these questions that we have. How do we allocate our money? Are we going to meet the goals we've set ourselves for exploration? Should I be exploring here? Should I stop exploring here? Okay. How much is this exploration really worth? So anyway, I'm going to get onto there's basically two main types of prospectivity model. There's a knowledge-based one, and there's a data-driven one. Knowledge-based is basically mineral systems modeling, which I'll go through first. Second is the data-driven one is machine learning. I'll then move on to our sort of a third approach that we're developing at SRK, which is based on the Bayesian framework, which I believe sort of integrates both. Before that, I'll give you a bit of background on mineral systems modeling and machine learning, and then go on to our own one. So, mineral systems modeling. Mineral systems is basically making a conceptual model of all the critical processes that you need for a mineral deposit to form. It aims to answer some of these questions we have. Where's that metal coming from? How is it transported? Why is it being deposited where it is? And okay, if it is deposited, what needs to happen in the next 2 billion years for us to actually find it here? Unlike machine learning, the other method we'll go through, we don't use any knowledge of actual where the deposits are to make our model. It's based solely on our conceptual understanding of where a deposit should be. And because of that, it's actually quite suitable for areas with low exploration maturity, where maybe we haven't made any discoveries, but also areas where there's perhaps less data available. That's not to say it can't be used in mature areas with lots of data as well. It's a bit more universal than machine learning, let's put it that way. To actually apply our conceptual model, we also must need to build like a practical targeting model, and I'll show you how we do that. So step one, and this is one we're probably, as geologists, probably more comfortable with, and that's a good old-fashioned literature review and compiling and construction of an up-to-date deposit model, or maybe you might want to adopt one which is already in the literature. You can also do that. Although it's a sort of traditional deposit model, we do want a sort of increased focus on the whys of why a mineral deposit forms, rather than the sort of knowledge of the signature of the deposit, although that is useful too. And the output from that is ultimately a nice shiny report for our clients at least. But really the deposit model is the fundamental of everything in exploration, really. So if you haven't got that, you're not going to get very far. So we've got a conceptual deposit model. This one was, unfortunately, I have to redact because it's confidential, but it was one that we constructed for lithium pegmatites. Sorry if it's not very smooth. There we go. Okay. And so to get a deposit model into a mineral systems model, basically we'll break it up into what I would call like 3+1 critical processes. We've got, the fertility, geodynamics, and architecture, and then my +1 would be the preservation, because sometimes it's not really easy to incorporate that much, and to me it's kind of conceptually different than the other three. And we want to organize, I think, them into a critical scale matrix. That's which processes operate at which scales to make a deposit form, and what of the underlying critical processes do they represent. The philosophy here is that if you don't have fertility, you don't have geodynamics, you don't have architecture, you're not going to have deposit. It doesn't matter how good two of them are, if one of them is not present, the deposit won't be there. Scale is always important to consider when we're in prospectivity here. And if we'll use different data sets at different scales here. So it's a nice representation of, and a good way to get your thinking clear on what operates at what scale. This is a very simple matrix. We made this for orogenic gold. This is one we sort of made in our own time, so it's very sparse, but some of the ones we make for clients are a lot more detailed. But to be honest, you normally get all you need from the real basics anyway, and I think I'll show later that it's actually quite powerful just using a simple set of ingredients. So the next stage is we've identified which processes, constituent processes, you need for a deposit. We've identified what kind do they represent, fertility, geodynamics, etc. We then need to put them into a targeting workflow. We use like a hierarchical model. So we need to, part of this, we need to identify what are the things you can actually map, which represent those processes. Then they're the things on the far left. And then we have to work out what are the relationships between different layers. For example, on the top left here, we have these two different fertility layers. We have metamorphic grade and proximity to favorable granites. We've modeled them as an either-or kind of relationship, whereas others, it's sort of they can work in unison to create a deposit. So you need to think about how these layers interact, and then how they might combine to represent the different critical elements, which will eventually lead to a deposit formation. Now we combine these layers together. The most typical way to do it at the moment is using fuzzy logic. Fuzzy logic is a sort of machine learning. I mean, the next slide is talking about that. And skip. Okay, no. Fuzzy logic is basically a way of us combining sort of disparate data sets, which are perhaps a little bit more qualitative rather than quantitative together, and make it so that the output is something between 0 and 1, so we can actually use it to map prospectivity. If you're interested in fuzzy logic, I advise you to look on the internet. There's lots of different things. It's using lots of different domains. But it's basically adding, what isn't the right word, but adding a bit of fudge factor so you can actually, get something which is perhaps categorical into some value between 0 and 1. And so we first fuzzify all our input values, and then we use these fuzzy membership functions, lattice functions, to combine the different layers together. And we do that at each layer of our model until we get our final output, which hopefully is on the next slide. Yeah. Well, first we have these intermediate steps where we combine to get our fertility layers, our geodynamic layers, our architecture layer, and we combine them at the end, and we have what we normally call our FGA layer, but it's our final output layer of the mineral system model. You see this one's got a little bit of a case of the measles, unfortunately, and that's probably due. I spoke earlier about scale. That's perhaps an indication that we've got something in there which is shouldn't be in here. It's perhaps the wrong scale. But just for a demonstration purpose, you can see how we can combine those layer scales to get our ultimate prospectivity model. And that's highlighting the areas we'd expect. I think Kalgoorlie's in here somewhere. Some of the Pilbara gold occurrences are up here, and there's a few gold occurrences in the Kimberley. So that's our main knowledge-driven method.
Quick question.
Sure, yeah.
What do you define as architecture?
Yes. So I did say at the start we're using public data here. There's one data set we're using which relates to the architecture we're using. There's a data set called the Global Lithospheric Architecture Mapping data set, GLAM data set. It's a paid-for data set. And what that does, what that data has is it's a global data set which maps mantle plumbing structures throughout the world. So the main control on orogenic gold is generally these mantle tapping structures. They're not found on the actual structures, but they're associated with them. In fact, a lot of deposits. I said I was working on lithium before. Same story there. But it's those mantle tapping structures. In fact, one of the things we kind of joke about is that a good area to look for lithium is basically a bad gold project. So they're quite related. Sorry, going off track there. So architecture is, it's basically our structure, particularly these mantle tapping structures, when we're looking at the regional level. Obviously at the more project level, then that might not be the case. Sorry, I should have gone to more fertilities. Obviously, is there the rocks here which could be the source of the metal? And geodynamics is, did it ever go into the right pressure, stress conditions for gold to form, as we believe it does? This is the zoom in, I think, of the Kalgoorlie area. The yellow dots are gold deposits. You can see there's a pretty good correlation between hot areas and gold mineralization. So, which is what we want to see. That hasn't. It's been squashed up. Anyway, another quick mention as well. We can do Monte Carlo simulation on these, so we have ranges of uncertainty on all our inputs, and we can flex them. And that can sometimes seem trivial, but when you think about what our big deposits are, they're at the tail of the distribution. So if you're just dealing with sort of mean all the time, you're really missing out on a lot of the value. And I'll speak a bit about that later when I talk about actual simulation. So that's the main knowledge-driven method for mapping prospectivity. And I'm going to talk a little bit about machine learning, which is pretty new to exploration. I think probably about 2015, 16, sort of first prospectivity models were coming out using machine learning in exploration. So it's relatively new, although getting more and more established. Now, unlike mineral systems modeling, machine learning doesn't use. Machine learning does use the location of known deposits to make the model. That means it is restricted really to areas where you have a lot of known deposits. You can't really apply this easily to a virgin terrain. Saying that, you could create a model based on a well-known terrain, say like West Australia, and then apply that same model to a different terrain, but there's no guarantee they're going to be exactly the same. And the philosophy of machine learning is basically let the data speak for itself. We use an algorithm which learns the relationships itself rather than explicitly telling them what the relationships. That's not to say that geology doesn't play a role. Geology still plays a role here. We've got to consider what data we put in. There are people constructing machine learnings out there who have the more expansive policy. Let's say they're just putting everything in. I don't think that results in good results. I think you should be a lot more selective about what you put in. Every data layer that we put into our model we should be able to feasibly explain why it might be correlated with gold mineralization. If we can't, it shouldn't go in. There's still a role for the geologist there in making sure our data is feasible, basically. We're going to go through a few of the steps to make a model here, so I'll go on. First step, we need to prepare all our data. This model is, I'm not sure if it's exactly identical layers to the mineral systems model? I think it is. If it is not, it's very, very similar. So first step is data preparation. We have to rasterize all our data so that it's on one consistent grid. I should mention everything we're seeing here is on 1 by 1 kilometer grid. And we'll normally want to use some kind of derivative of the actual feature. So what we're seeing here is north-south structures. If we just use north-south structures in our model, it wouldn't work because, basically you're on it or you're not. So we have a sort of distance to feature. So the top map there is distance to these north-south structures. But also is where the geological knowledge comes in again. Like, if you look at the scale there, that goes up to 200 kilometers now. If you're 200 kilometers away from the feature, does that really have any impact? No, right. So we cap it, basically. So that's the one which would go in that bottom left-hand one. We've capped it at 10 kilometers. I mean, even at 10 kilometers, I think you're pushing it a bit. Does a structure really have that much influence? Because these are the smaller, these aren't necessarily the mountain tapping ones, which would probably have a bigger. So we would use different caps for different data sets, and again, that's where the geologist comes in. Now, the next stage is we've got different layers. We want to see if they actually do correlate with gold mineralization. We think they might, but we don't know. So we've got a whole heap of different layers here. Only a fraction of them did we actually use. And that's because some of them, when we actually look at do they correlate with mineralization, they don't. If they don't correlate, just not put them in. And we do that individually, and then we also look at them collectively, and we also try to avoid really highly correlated data, which are basically mapping the same thing. If we have really highly correlated data, basically pick the best one. If we have data which doesn't correlate with our mineralization, or we have sort of matching data, very high correlated data, we can get a lot of noise. Even worse, we can get spurious anomalies. So yeah, it's bad news. We don't really want to do it. So it also, if the more data sets we give it, the more likely it is that we could overfit our model, which is something I'll get to in a minute. So our next stage is to train our model. This is where the algorithm takes over. So there's a few different algorithms we can use. The most common is random forest. I'm not going to go into a huge amount of detail about exactly what that is, but it's basically creating a lot of different, thousands of different decision trees, each which has a different view of the data. It sees different parts of the data and weights them differently, and then sort of lets them vote on what's important. But basically, the feature of machine learning is that the algorithm improves itself. It learns itself, and we don't actually input how it should be. That said, we make lots of models, and it's a very iterative process. So we make a model, we look at it, we see is it working effectively. We take layers out. We change what they call the hyperparameters of the machine learning. That's I talked about random forest there. We have lots of different trees. We can tell it how many trees. We can tell it how many levels the decision tree should have, and that kind of thing, and how much variability there would be in what the different trees can see. Sorry, I won't get too much into the weeds on that because it's the weeds. Okay, but it's a very iterative process. Typically, we might go for like 9 intervals before we arrive at our final one. Sorry, I missed a step on the earlier one there. We train our algorithm on the subset of the data, our training data set, and we look at it, how it performs on the testing set, which typically the training set might be 8%, and the testing set 20%, to see if it actually is working as we expect, or if it's just picked up noise in that set. One thing we can do is split data spatially. So on the left there, that's different gold mineralization sites in Western Australia. We can cluster them, so we have spatial clusters. And basically what we do is we had 10 clusters there. We we compress them into 5 different clusters, and then we train the model each time, leaving out one of the clusters. We said that's our testing set, and then we train the model on the remaining 4 and see how it performed on the last. And these are ROC graphs. I'll get to what they are and how they work in a bit, but basically you want them to be as much as a right angle as you can. And we can see this one is perhaps not. That's actually an indication that this area is probably a bit different to the rest. And in fact, this fold 2 is actually this Kimberley region in the north of Australia, and it probably is actually a bit different. The mineralization might be a different era, and it's a good thing to bear in mind. You should always try and just model one mineralization event at once, otherwise you'll get a poorer model. So I think if we were doing this for a client, we'd say, look, this is obviously a different region. Let's just split it out and make a different model for that one. And the client might say no because that would be more money. Anyway, we can carry on. And so here's our final machine learning model. What it outputs is a map of relative prospectivity. So a score between 0 and 1. 0 is not prospective, 1 is prospective. And yeah, that's our final output. Obviously, the hot areas on the map are the better areas. Okay. One of the nice things about machine learning is it can actually identify relationships between the layers that we wouldn't have known, that we didn't previously know. But to actually make use of them, we have to be able to explain our model. Say, why is the model making this area prospective, this area is not. So we call it explainability. There's a few methods we can use that, but it is quite dependent on the algorithm we use. And one of the reasons we use random forest algorithm as opposed to some others is that it's quite explainable, the results. So this is an example of some of the data we can get to explain why some areas are prospective or not. This top right here is an example of what we call a Shapley diagram. So basically, the color is whether that feature had a high value or low value, and the Shap value here is whether it was how important it was to the model. And that can be either positively or negatively. You can have a layer which just says this is very unprospective. We can see at the top there we have this distance to orogenic belt. I think that layer is. So basically, you want a very low value. You want to be in the orogenic belt. So that's why the really high values are correlated with the very dark purples in that diagram. And yeah, that can help us explain why areas are what they are. One of the things we use is just the sort of feature importance, and that's the same which layers are basically the most important in our model. Okay, so that's the 2 main sort of, I want to say, traditional ways of prospectivity. We are developing our own sort of integrated approach based on Bayesian probabilities. So I'm going to just talk to you about that a bit. Before I do that, I guess it's a bit of exploration philosophy I'm going to give. But how would you actually manage exploration at the moment, and why might we want to take a different approach to mineral systems and machine learning? Okay, so what do? We have that area we want to look for. We identify a prospective terrain. We generate a load of targets on that terrain. We rank our targets, saying this is our best. It's, you can go down our ranks here and start an exploration. And we keep going down the list. And eventually, we're a junior explorer, so we run out of money and go bust. Or we give up, anyway. But unfortunately, we don't really know. Somewhere there's an economic cutoff, right? Somewhere along this line, there's a point where we shouldn't be exploring, but we don't know where it is. And that's why exploration is inefficient. Our traditional prospectivity models don't really help us in this regard because they're all relativistic. They don't actually tell us, okay, this one's better than this one, but it doesn't tell us by how much. Furthermore, it doesn't tell us where the line is. one of the perverse things about things like machine learning is it can be quite value destructive in that it can just cause you to get more targets. And if you just make this list longer, then you're just going to lose more money. So we don't want to do that. So we need a sort of different way of looking at this. Just saying more of the same kind of thing. Basically, you've got your map. You're looking for your mine. Is it here? Is it here? Then you realise actually we're part of a bigger terrain, and the best areas are down there, and that's where the mines actually are. So you've got a tiny mine, or worst, a really tiny mine. Basically, the philosophy here is prospectivity isn't about trying to generate more targets. Geologists are perfectly capable of generating targets themselves. What we need is to actually be able to quantify how good our targets are and use that to deploy our capital in an efficient way and drill only the things which should be drilled. So this is this diagram right here is actually I look back from when we very sort of conceived of what we wanted to do. This is what we had. It's like we want a map where each cell has a probability distribution of what you're going to find. That we can use that then to actually decide what we should be doing exploring here. And we term this absolute prospectivity. So it's like, okay, let's try and make that. And we actually paired up with Exeter University, their Department of Mathematics and Statistics, so this is our problem, can you help us? And we set up a research partnership with them. It was funded 50% by the UK government. It was a 2-year research partnership, and this is basically sort of what we came up with. And we call it MVAP, and it stands for Management and Valuation through Absolute Prospectivity. We had a more snappier title, but was informed that someone had already used it. So that's what we came up with. The good thing about this is it combines sort of both the knowledge-driven prospectivity I talked about first, but also elements of machine learning as well. There's elements of data-driven there. It's a nice kind of hybrid method, and I expect some of you kind of know a bit about Bayesian probability. But basically what we're trying to do is we're saying, okay, the mineral system is our prior expectation. That's where we think things should be. But we also have the evidence. That's where deposits actually are. But there's actually some other parts of the evidence as well. There's, where have we actually looked? And we're trying to combine them using Bayes' theorem to get a posterior probability. So that's basically, in a nutshell, that's what we're doing. So I'll run through the steps of how we actually do that. I'll skip the slide, actually, it's not too urgent. I tanked the presentation. Sorry, excuse me.
Do you want that other?
Yeah, sorry. Skip the next slide. There we go. So the first thing we need to do. There we go. The first thing we need to do is we need to get a mineral systems model. We need to turn it into a mathematical representation. That there was made with fuzzy logic. Unfortunately, fuzzy logic is exactly that. It's fuzzy. It's not real logic. So we need to actually turn it into maths. You could also use any kind of input here, really. You could use, we've done it based on a weights of evidence kind of prospectivity model, which is a sort of a bit more old-fashioned kind of model. You could even use it on basic interpretation. But anyway, all we're trying to do is we're trying to recreate that mineral systems map here as a mathematical representation. So the algorithm here is just churning through, trying to basically get everything along that line, just basically saying, okay, our mathematical representation is the same as a more qualitative representation. And we do that through machine learning, basically. These are the parameters of the mathematical formula we've said describes mineralization, basically. So you can see it's trying to optimize them and find something which gives you the least error. Yeah. We actually model it as we use logistical regression. You can use more sophisticated things if you're mathematically inclined. Okay. So this is step 2. I was in 2 minds about including this actually, because this is actually kind of more of an optional question. But it's actually something worth doing in any kind of, anytime you're looking at regional exploration is endowment modeling. So what we're saying is we have a terrain, how many deposits are there actually on the terrain, and how are they distributed? So this is West Australia. It's a bit blurry, so you might like to see, but the light sort of salmon pink here is deposits we found, and we can use this method SIP's law to try and say, well, we can fit a distribution to it and say, well, which ones haven't we found? That's what I've used, tend to use. We can also look at a time series endowment kind of model. We can say, okay, well, what did we discover each 5-year segment and project that into the future until it looks like we're not going to be finding anything, and say, well, that's our endowment. Or there's sort of more qualitative methods as well, a USGS method, which is basically we decide. A bunch of geologists decides. It's a bit more sophisticated than that, but in West Australia, our endowment modelling tends to suggest probably about 60% of all the deposits have been found. The remaining 40%, probably there's a decent chunk which will never be found. They're just not discoverable, apart from by random chance. The deposit has a thick layer of sand on and doesn't have a big signature. It's not a big deposit. You might never find it. I would say probably if you exclude the what's not discoverable, we're probably in the last 10-20% of deposits to be found in West Australia, gold deposits. It's about as mature as you can get in the world for gold exploration. So we construct our endowment model, which tells us how many deposits and how big they are. This hasn't displayed correctly. Let's see. Some of these slides might not display correctly, but I'll explain what you can't see. Basically, the next step is to create a data matrix. So we get all our data layers in one matrix. We also want to collect some other data. We want to collect where we've explored. So this map here is actually a map of exploration intensity. So we've said, well, how many times have we actually explored in this area here? So this scale is actually, we did that by looking at how many exploration reports are filed, because in Australia you have to file a report each year. So you can see in here, this area has been like over 100 reports. Basically, as long as it goes back, there's been people exploring there. No one explores here, desert. We can use that to say, oh, how intense is the exploration here? This is actually kind of a key advantage over machine learning, in that we're building an evidential map, not just based on where the deposits are, but also where we've actually looked. One of the I want to say the dirty secrets of machine learning is that you have this what we call the non-deposits problem. And that if you really want to train an algorithm, you have to give it positive examples, but you also have to give it negative examples. And it's not really they don't really exist. We don't go to the effort to completely drill 100 holes to absolutely prove there's nothing there. We may drill a few, but there's probably a reason why you drilled there in the first place. So the probability that there is something there is non-zero. Now, in machine learning, we get over that by we say, well, these areas which we don't think are prospective, they're not prospective. But we're just biasing our model doing that. Or might say, well, a better approach might be like, well, if there's a coal mine here, there's not going to be a gold deposit. It's true, but how many coal mines do you get in the gold terrain? None. So there's no real satisfying way to get over that problem in machine learning. So generally what we just do is pick a bunch of random points and we rely on the fact that mineral deposits are rare and say, well, those are the non-deposits. But that's obviously not really correct. So, but we can do a better job here because we say, look, what we're trying to do is we're trying to score the whole map between 0 and 1. We're saying, well, where there is a deposit, that is a positive example. Where there isn't a deposit, but we've done lots of exploration, well, that's closer to zero than a place where there's not a deposit, but we haven't done any exploration. So we're basically using the intensity of exploration to not to say 0, 1, we're saying well, somewhere between 0 and 1 in terms of is it a deposit, isn't it? And so that's why we bring this layer in. Oh, is it working now? Yeah. This was what wasn't shown before. So we have our matrix of our data. This is our count of, so each row on this is basically a cell of the map, a 1 by 1 kilometer cell. We count how many drill holes are in each cell. Drill holes. And we say if there's any mineralization in the cell. We actually use a bit more of a sophisticated mineralization map than we did elsewhere. I'm going to show us that. So, take my word for it. And this is our, how many reports there were on each cell. How many years have we explored that cell? Each one is 1 by 1. Yeah. I think in Western Australia that results in, I think Western Australia is 2.5 million kilometres squared. So this. So we're going to report back to the bigger area, to the 1 by 1. Yes, yeah. So we basically had Western Australia provides polygons of where the report covers. Right. And you can just layer those polygons up and you can say, well, and they've each got a date attribute, so we can say this was explored, 1970 to 1978. And, yeah. This isn't possible everywhere because West Australia is kind of unique in how much data they give you. But I think you could probably look at other proxies for exploration maturity, even just a qualitative. So where you've got areas where there is nothing. Yeah. Yeah. What do you do with those? So they get we don't use them to construct our model, but we can build the model and still interpret the values into them after. Yeah. But they're obviously going to be low prospectivity areas. Exception might be if it's a high prospectivity area in a national park or something like that. Yeah. Well, and that should then still show as prospective. Very prospective because it wouldn't have been explored. Okay. So this is actually the bit which takes a lot of the time of actually making the model. There's a few additional parameters we're putting into our model as well, and they are basically because we're using it for where we've done exploration, also where we drilled. We need to know how efficient is a drill hole. If we drill a hole in a 1 by 1 kilometer cell, and somewhere in that 1 by 1 kilometer cell there is a deposit, how likely is it that a hole will hit it? We're making an assumption here that the holes are somewhat guided, that geologists are reasonably on some kind of reasonable playing field here, but just a few different assumptions. But so we can infer some of that from the data and put some uncertainty around it. And yeah, same with if you do grassroots exploration, if you do 10 years of grassroots exploration, what's the likelihood if there was a deposit there, you'd uncovered it. So we can make some estimations of that. We do that by size class as well. So a big deposit's easier to find than a small one. Unfortunately, it's a lot fewer of them. But yeah, they normally have big signatures, so they get revealed in the data. Endowment modeling, actually, when we look at sort of the time series endowment, we find all the big deposits, not all of them, the majority of them in the early years of exploration. So the Golden Mile was discovered over 100 years ago in Kalgoorlie. Everything we find, that's one of the features we can use actually to model, is that we can hang a distribution of that biggest deposit in. It's a different subject. So we're modeling these extra parameters. These are actually quite useful because we can use them afterwards. I'll show that. We're putting that into an algorithm. We use Stan, the Bayesian modeling software. Which can sound complicated, but all we're basically trying to do is we're saying, look, the probability that there's mineralization is basically the probability that we think there is mineralization, our mineral systems model, basically. Times sort of discovery. I mentioned that some deposits are never going to get found, so let's say that's something like 8%. We're plus times the sterilization factor. If we explored a lot here and we haven't found anything, that probably indicates that there isn't something there with a certain level of uncertainty, and also a sort of false positive rate as well. So basically the Bayesian model is saying, well, that's our formula. We've got lots of different parameters. We'll just optimize that. So we're saying the computer is basically trying to optimize what those parameters should have been to best conform with the evidence. The evidence of where the deposits are, where we have done an exploration. So that's what we did. This image here is basically showing the difference between our prior model and our posterior model. So our prior model is our mineral systems model. So you can see it's actually depressed the prospectivity a little bit in the sort of more desert areas and enhanced it a bit more in the actual gold belt, which is probably a good thing. These are the actual parameters of the model. So this is prior, this is posterior. You see, hopefully, we're trying to get a sort of slightly tighter distributions, which we have in some of these. They're actually quite similar. And that was because our mineral system model was great. So it hasn't actually changed that much, but it has changed a little. These are just the histograms of the actual values across the map. So you'll see blue is our posterior, so our Bayesian model, and pink is our prior model, i.e. our mineral systems model. The left is just the cells where there is mineralization. You see it's actually scored them a bit higher, which is what we want. And this is all the cells, and you can see it's actually it's subtle, but it's actually a bit more of a binary classifier. There's more absolute, this is definitely unprospective, and this is very prospective. It's not a huge difference, but there is a bit of difference. So I mentioned that we basically estimated those parameters of how efficient our exploration is. They also get optimized during that process, saying, well, what we said it was 70%, but it's actually could be 75%. We can use those values to actually explicitly sterilize our map. What I mean by that is we can say, well, if it's a 90% chance that a drill hole is going to intersect a deposit if it's there, and we've drilled 10 drill holes, I don't want to do the maths, but it's a low probability that there's now there mineralization there. So we can use that to sterilize our map, and that's what this is. So it's not showing exactly right, but anyway, you can see this is the Kalgoorlie area. It's sterilized that. It's said it's basically been done to death. It's very low probability you wouldn't discover anything. Other areas of the map, I think this is a national park here, which is why it's still showing as quite prospective. The Yamana belt is still quite prospective and nothing to explore. I'm in trouble. Oh, we have something pop up here.
That's nothing to do with you.
It.
Pause it.
Yeah, it's from me, but just can't close it. I'm not sure why that's coming up. There's actually information behind this map, and it's not displaying. Sorry, almost at the end. Okay, do you want to see if we can skip it to the next slide? There we go. Yeah, I can take it a minute. It's fine. So, I mentioned that a lot of this data is size dependent. The probability that you're going to intersect a deposit with a drill hole, let's say, is higher if it's a big deposit. And so wherever we can, we size segment our data. And it means we get a size segmented model. So in this example, this blue polygon you can see on the bottom of the map there, that's the area. These are the outputs from that. So these are the probabilities that there's undiscovered mineralization in that polygon of these different size categories. Estimated probabilities, I should say. This is actually it's hard to see on the map, this is actually a very large polygon. This is over 30,000 kilometers squared. The biggest license in West Australia is currently about 2,000 kilometers squared. So, yeah, typically you're dealing with much smaller probabilities than this. In fact, you know, a typical license probably, you know, you can divide this by about 1,000. But anyway, if you're, let's say you're a big gold company, you're Barrick or something like that, you may have some overarching exploration goal, what house discovery. We want a plus 10 million ounce discovery every 10 years. And you can use this tool to say, well, you know, we're going to need about at least 5 of these if we're going to meet our goal. And you could use that to defend your exploration budgets, or you could use that to say, look, we need to have more land, we need a bigger department. Those who work in exploration know the problem with exploration is that every 5 or 6 years, everyone gets sacked and they close all the exploration down when the market goes bad. So this could be perhaps some inoculation against that. But anyway, yeah, we can use this to sort of forecast what's the probability that we actually might discover what we want to discover. Let's see. Yeah, you'll notice when we're estimating things like these are the coefficients of the geological layers in our model. They have a range on them. They're not. We don't just use the mean, so we can actually flex the model and model. Okay, it could have been this, it could have been that, and come up with a range of values across that map. This is really important because you know, in exploration we're all dealing with the tail of this distribution. We expect to find nothing. The deposit exists in that very slim chance we find something, and in fact the value in exploration comes in the even slimmer chance that we find something big. So it's actually really quite important to try and classify the uncertainty. We can use that. We can run a simulation, look at the different outputs. We can put values on all the different scenarios that the simulation implies, and then probability weight them to do things like value. And this is a very sort of crude valuation model, but we're saying, okay, it's a one period, basically the period it would take from do all the exploration on this area, you know, about 10 years perhaps, and we're assuming that we just went and did all the exploration. What's the value of the project? Comes out about 100 million, which actually intuitively is probably about right, given this is 30,000 square kilometers. If you told me the biggest exploration license in Australia changed hands for about 1 million, that would feel about right. And this is just the grassroots undiscovered potential. Obviously, if you have deposits in this area, then you'd value them separately. But anyway, this is just about the undiscovered potential. So we could use this for testing, whether valuing. We could also use this as a sort of a sandbox for testing out different exploration strategies. You know, when should we stop exploring, etc. Okay. And also, yeah, same kind of data we can use to make those tough decisions that no one wants to make. You know, should we just stop exploring? If we have an area of very low probability of success, we can just say, well, let's drop it quicker and actually quantify our decision rather than doing one punch. Okay. This is actually, and this is, yeah, apply the values. This is every exploration license in Western Australia, which is tagged for gold. So you can do it across the whole and say, okay, where are the best licenses? Yeah. Okay. Right. So we've shown a few different models there. I just want to close basically by saying, well, how good are our models? So as a quick exploration model efficacy. You've probably seen a few of these throughout the presentation. This is what we call our receiver operating characteristic curve, a mouthful, ROC curve. We also often have this metric, AUC metric. This is actually common to all machine learning. This isn't just prospectivity. It's common to all domains. But basically what we're saying is, you know, what % of the area do we need to capture what % of deposits? So in an ideal world, it would be just go straight up to the top and then, you know, be a right angle. You never get that, but and if you did, you'd be a high suspect. And this dotted blue line is basically, that's just random chance, right? If you had absolutely no idea, you just go along that blue line. So we can use this as an indication of how good a model works compared to another model. And look at this AUC metric as sort of how they work. So these are actually our 3 different models you've seen through here. The MSM model, the machine learning model, the Bayesian model. They actually all have exactly the same AUC value. So you can say it doesn't actually matter too much which model you use. You're probably they're all about as effective as each other. What really matters is the data you put in. Right? If you put bad data in, you're going to get the old thing, rubbish in, rubbish out. It's always true. This shows we shouldn't get too anxious with exactly what model we're using. They're probably going to give us very similar results. I think that's the advantages of what can it tell you, right? Which of one can. Machine learning might have to give you knowledge of new relationships that exist, and that can tell you this, what is prospectivity, what's the absolute prospectivity, what's the actual probability. So they have different uses, but they're very similar in what they highlight. And just a quick warning as well on these ROC curves. They're quite easily manipulated. Just treat them with caution, especially when it's someone trying to sell you on some new whiz-bang machine learning method. These are actually exactly the same model. I should have got one with actually a bigger difference, but this is exactly the same model, 2 different scores. This one looks slightly worse. And the only difference is because this is just restricted to the Yilgarn, and that's the whole West Australia. So if I wanted to make my model look absolutely fantastic, I would have just included a load of ocean. Because our model was very good at saying there's no minimalization there, and it would make our model look it would flatter it. So yeah, ask yourself some questions when you see one of these. Say like, well, what is the actual area? And if it's got a load of unprospective area, it's going to make it look way better than it wouldn't. So this is actually the more realistic one on the right there. Say, well, there's quite a lot of unprospective ground in West Australia as well, right? So just be a bit wary of that. Okay, I got one slide here on targeting. This is the last slide. So just we often want to try and combine all these different outputs. One of the nice things, because we're actually using the same data, the big challenge is cleaning the data. And once you've done that, let's say you've made your mineral systems model, it's actually quite trivial to do a machine learning model or a Bayesian model. You've done all the hard work, so you might as well do it. We generally do all 3 if we can. And what we generally do when we're trying to actually generate areas for our clients to go and explore, we'll use the MS mineral systems and machine learning. Because they're sort of at the 2 extremes, if you like, to actually generate the target areas. And we keep the MVAT back in reserve as the sort of adjudicator. Because obviously, if we're using the prospectivity from machine learning to say how good is a machine learning project, it's like, well, it's marking its own homework. So it's good to have these 3 different methods, and we can sort of get the best of both worlds. At this stage, we've also put in a lot of other things. We've got some detection data. Maybe we have some geochem. We might try and sort of quantitatively use that as well. ESG, infrastructure, we can use them to modify our opinion on whether we should be exploring here or not. And we generally workshop it with our clients, say, well, these are our ideas, and come up with our final recommended areas. You could do a whole presentation on this, but just to mention that normally there's a bit of work on, we don't just give them a map and say, get on with it. That's that. Okay, I think that is the last slide. I'll, of course, be happy to take some questions, and yeah, thank you for your attention.